In this lesson, we're going to explore the graphs for tangent x, cotangent x, secant x, and cosecant x, with the goal of actually drawing our own graphs if we're given an equation. So let's first take a look at the parent graphs for each of these equations, and then also some transformations that we can perform for these. So I've graphed the equation y equals tangent x, and I use Desmos to draw this, and you'll notice that the graph has a particular periodic shape. The period is one of these, the period is the length of one of these cycles. And these cycles kind of almost look like the old x cubed graph that you may be familiar with, but they repeat. And the length of that cycle happens to be pi this time. So if you've studied the y equals sine of x or y equals cosine of x, you probably know that the period of those functions is 2 pi. But oops, that's a terrible little bracket there. But the period for this tangent function is pi. I also want you to notice that this graph includes some interesting asymptotes, vertical asymptotes that occur at negative pi over 2 and pi over 2 and 3 pi over 2 and so on. And we're going to use those asymptotes to actually zero in on where the graph should be located. Finally, there's one other interesting point, and that is this little Reef inflection point here where we have the rotational symmetry. So if we were to actually take this curve and rotate it 180 degrees around this point, it would look exactly the way it looks now, which is it would still have this shape. The other thing I want you to notice about the tangent function is wherever these asymptotes are, on the left it starts low and moves to the right where it ends up being high. So we go low to high for a tangent function. That's going to be important because later when we study the cotangent function, we're going to see that it goes high to low. Okay, so the important features of this graph are, first of all, that shape, the blue shape, which is sort of like an x cubed. We have these vertical asymptotes that are the boundaries for each cycle. The width of the cycle, which is called the period, is pi. And that's different than a sine and cosine, which have a period of 2 pi. And finally, this curve has rotational symmetry around this inflection point, which is located at 0, 0, or pi 0, or 2 pi 0. It's smack dab in the middle of the asymptotes. It's halfway between the asymptotes. So that's the tangent function graph. Now, let me show you how we can put the same sort of information into this equation that we did for sine and cosine and transform this thing. We can stretch it, we can change the period, we can translate it around the coordinate plane. And we do that by introducing some extra numbers into the equation. Here's what you get when you do that. So here I've graphed a function that's been transformed. And in general, you'll remember that our transformations had the format y equals, and then we had a multiplier out in front. For sine and cosine, we called that the amplitude with a capital A. Then we had our function name. In this case, it's tangent. Then we had our k value, which helps us compute the period. Then we have our variable, either x or theta. And then we have on a shift value that helps us compute the phase shift. And then we had I'm running out of colors here. We'll just make this one black, I guess, or yellow. I can do yellow. Then we had a vertical shift number, which we called h. And just like the sine and cosine functions, these numbers play similar roles. I'm going to start with the vertical shift h here. Notice that we had a +1, and what that did is that moved our midline up to 1 unit. So this orange line here is drawn at y equals 1, and now that inflection point is going to be located between the asymptotes using that line. The period for tangent and also for cotangent is computed by doing pi over k. For cosine and sine, it was 2 pi over k, but for tangent and cotangent, it's pi over k. So our original period was pi. Our new period is pi over 2. The distance of one cycle, like this one right here, instead of being pi, it's pi over 2. And all the cycles have a distance of pi over 2. Look at this one here. From pi over 2 to pi, that's pi over 2, right? So regardless of which cycle you look at, it has a width of pi over k, and we use that 2 to compute that. The phase shift is a combination of c and k. Just like we did with sine, if you want to do the phase shift, you do the opposite of c divided by k. In this case, for us, that would be positive pi over 2 divided by 2, which is pi over 4. So there's an adjustment here to the right of pi over 4. And you'll notice that in these points that we've drawn, the inflection point that I mentioned from the other graph, instead of being at 0, 0, it is shifted over to pi over 4. Now it also shifted up to 1 because of the vertical shift, which is the one we already mentioned. And finally, it's a little less obvious what this 2 does. But what you'll notice is the bigger that number is, the more stretched out this curve gets. So as that number grows, the curve is less curvy. It's straightened out more. That's a terrible drawing. Let me undo that. It becomes less curvy. So it takes longer for the curve to approach these asymptotes. If this number is less than 1, if it's smaller, then the curve gets to the asymptotes quickly and it's really curvy. Something like that. Terrible drawing, but I think you'll get the idea. So we can manipulate these graphs the same way we did with sine and cosine. The only thing that's a little fishy or different is that asymptote value. It doesn't really represent the height of the function, but it represents whether it's stretched or compressed along the y-axis. Now, the same thing is true of the cotangent function, but I want to show you the parent graph so you can see that there's a couple of distinct and important changes. In particular, pay attention to where these asymptotes are on the new function. So here I've graphed y equals cotangent of x. It has a similar feel to y equals tangent of x, but there's a couple important distinctions. First of all, notice that the graph is going in the opposite direction from left to right. It starts high and it goes down low, right? Whereas the tangent function started low on the left and high on the right for any cycle. The other thing I want you to notice is that these asymptotes are in different locations. They are at negative pi and 0 and pi and 2 pi instead of negative pi over 2 and pi over 2 and 3 pi over 2 and 5 pi over 2. Those values where the tangent's asymptotes are where the cotangent's inflection points are. So the asymptotes are in a different position and the curve goes in the opposite direction. Other than that, all the same things that you can do to a tangent function, you can do to a cotangent function. We can stretch it out with an amplitude number. We can do a change in period. We can do a phase shift, and we can do a vertical shift. Okay, let's take a look at the secant and cosecant functions before we actually start to draw our own graphs. So this is the parent function, y equals secant of x. It has some interesting features, but one of the things I want you to know is that this function is actually related to its reciprocal function, the cosine function, and I'll show you how. The cosine function, remember, starts up here at 0, 1, and then it heads down towards the x-axis and crosses at a 0 at pi over 2, the exact same place that the secant function has an asymptote because 1 over 0 is undefined. It hits a low point at pi, and it crosses again at 3 pi over 2, and then it gets high again. And so these high points are exactly the places where these U-shaped graphs have a vertex. And the low spots are exactly the place where the upside down U graphs have vertex. So secant is closely related to cosine. Another important characteristic of this graph is that the cycle has to include one of the up scooping u's and one of the down scooping u's. So a complete cycle is from negative pi over 2 here all the way to 3 pi over 2. And that distance is 2 pi, just like cosine. To get a complete cycle, you have to start at one asymptote, pass the second one, and go to the third one before you get a complete cycle that then repeats. So it goes high, oops, wrong graph, wrong pen, high, low, repeat, high, low, repeat. That's how this thing is set up. And again, just like we can move things around and stretch it out and compress the period and the starting points for this function, we can do the same thing for sine and cosine and tangent and cotangent. We can do the same thing for secant and cosecant. So let me show you how those transformations affect this graph. Then we'll show you cosecant, and then we'll be ready to draw our own. So just like we earlier transformed a tangent graph, here is a secant function. And I want to point out a few interesting parts of this because we're going to use this to draw one of these graphs. These are not that easy to draw, but once you get the hang of it, it'll become a little easier. First of all, remember that the secant function is related to the cosine function. So wherever that high point would move in a transformation of cosine, that's where these vertex type points for the upward scooping branches will be located. And in particular, we did a vertical shift of 1. So I moved the center line, the midline, up 1, although I didn't graph it. I moved it up 1. And then I used the amplitude measure to figure out where those graphs are going to start. So from the midline, we're 3 up to get those, and we're 3 down to get these bottom ones. So that 3 is kind of important, more important for a secant graph than it was for a tangent graph. We still have the same old change in period. So remember, for secant and cosecant, they're just like sine and cosine. It's 2 pi divided by k to get the period. So we would have 2 pi divided by 2, which is 1 pi. Notice that the complete cycle of a upward one and a downward one happen in the first pi units. We also can do a phase shift. In this case, we'd be shifting positive pi over 4. And that's easy to show if we remember that the original graph started on the x-axis, and this new one starts halfway between pi over 2 and pi over 4. Pi over 2 and 0, which is pi over 4. So this is pi over 4. So that's my phase shift. So that makes sense. That starting point moved. Okay, so the bottom line is that we can transform these graphs the same way that we would a sine and cosine graph. We'll talk about exactly how to perform this when we get to the graphing. Keep in mind that the important lines here are the vertical asymptotes, and I'm going to show you exactly how to find those. And then these max and min lines on the cosine graph become very important for the secant graph because that tells us where our branches are going to be located. Before we get to the graphing, let me show the cosecant, and I'll point out the changes from the secant. So I'm going to briefly point out the differences between the cosecant graph, which you see here, and the secant graph, which we had in the previous slides. So look, you'll notice it has basically the same shape. There's a top branch and a bottom branch, but the difference is where these asymptotes are located. So we have vertical asymptotes at 0, at pi, and at 2 pi, instead of negative pi over 2, and 3 pi over 2. The period is still 2 pi, right? It still takes this much real estate on the x-axis to get a complete cycle. And all the same things that we can do to a secant graph with the transformations, we can do with a cosecant graph. So I'm not going to show you another one of those because we're going to practice graphing some of these in the last remaining slides. So let's get to that before you fall asleep and stop watching my video. So if you were in class if you were in class, then we made this little chart that helped us graph all of these functions. And so I just want to point this out to you here. You can add this to your notes if you want to pause the video. But we have this sort of standard form for all of these trig function equations, regardless of which function it is, sine, cosine, tangent, cotangent, cosecant, or secant. They all have this format. And we've practiced picking out the A and the K and the C and the H and using them. But the difference with these new graphs is the asymptotes. The asymptotes are the key to getting a quick sketch of the graph. What I've done here on the left is I've made a table with all the locations of the original asymptotes for the parent function. So if you didn't do anything funky and you just said y equals tangent x, these are where the asymptotes would be located. And that is a great place to start when you're trying to draw these graphs. And you can see cotangent, the asymptotes are 0, pi, 2 pi, and 3 pi, and same thing with cosecant. And then I've listed the secant asymptotes as well. The thing is, our new asymptotes, when we do the transformations, are not located in those spots. They move around. That's where my little formula over here comes in. To find the new asymptotes for your graph, you take the old asymptote, you divide it by k, and then you add on the phase shift. That gets you to a new asymptote. Once you have a new asymptote, you can use the period, which for tangent and cotangent is pi over k, or for sine, cosine, cosecant, and secant is 2 pi over k. You can just use that period to figure out where the next one is. And then you can set up those asymptotes and draw in the shapes. It might not sound well when you're just listening to it and not looking at it. So let's start with a couple examples where I'll run through this process. So we're asked to graph y equals 3 cotangent of theta over 3 minus 2 pi over 3 plus 2. Our strategy has been to, first of all, make a list of the information that's important for this graph. In particular, the a value here is 3. To do the period for cotangent, it's pi divided by k. So in this case, k is 1/3. So pi divided by k would be 3 pi. The vertical shift is just the 2 here on the end, so that's just up 2. And that's important for us to know because that's where our little inflection points are going to be located for a cotangent function. So I'm just going to indicate that with a dashed in axis there. And then the phase shift. The phase shift for this graph is going to be 2 pi divided, 2 pi over 3, positive 2 pi over 3, divided by 1/3. That's going to be a positive 2 pi. Because c here equals negative 2 pi over 3. We do the opposite of c divided by k, and we end up with, as I mentioned, 2 pi. So in particular, we have a phase shift of 2 pi and a period of 3 pi. That's going to be important. Now, whenever you're drawing these graphs, you want to locate the new asymptotes and dash them in. So for cotangent, my old asymptotes are listed here in this row right here. So I'll just start with this old asymptote of x equals 0. I'm going to do the transformation, and I'll find out where the new one is, and I'll dash it in. And the transformation is the old one divided by k, which is 1/3, plus the phase shift, which is 2 pi. 0 divided by 1/3 is still 0, and when you add 2 pi to that, you get 2 pi. So my new asymptote, the one that used to be 0, is now at 2 pi. And I'm going to dash in, right down the 2 pi line, that asymptote. Once you have that asymptote down, we know there's another one when we add 3 pi onto that one. So every 2 squares is a pi, so if I'm at 2 pi, when I go over 3 pi, that's 1 pi, 2 pi. 3 pi is actually out here where 5 pi would be, but it's a little bit off my chart by 1 square. And that's where the new one is. And then if you were to go backwards, you'd end up with a another asymptote 2 squares past the x-axis if you want to see where that one was. Okay, now the last thing we need is that inflection point. For cotangent, it used to be at pi. Now it's going to be at 7 pi over 2, which is halfway between my two asymptotes. From there, I'm essentially going to fake this graph. Now, because this asymptote is 3, or this, amplitude is 3, this number, that's a pretty big number. It's going to stretch my graph out a little, so I don't want to make it too curvy. So this part's going to come off something like this and head that way, and this part's going to go like this and head that way. And then again, I'll have basically a similar situation here where my middle point is here, and this one will head off this way, and this one will head off this way, and it's off the graph. We're just trying to draw a sketch, so these don't have to be perfect. Basically, we want to make sure you have that new midline and then the asymptotes drawn so you can sketch in the shape. I'm not saying I'm going to win any art awards for these graphs, but this is a pretty good representation of the cotangent function with these changes. Okay, let me just do one more because the secant and cosecant ones are a little bit more complicated than the tangent and cotangent ones. But the idea is the same. Locate the asymptotes and draw the picture. So in our last example, we're trying to graph y equals 2 secant of theta over 3 plus pi over 3 plus 2. And as usual, we start getting organized by listing our information. The A number is 2. Since K is pi over 3, I'm going to do 2 pi divided, or excuse me, since K is 1/3, I'm going to do 2 pi divided by 1/3, which is 6 pi. My vertical shift is up 2, so that means there's a new midline here, and I'm barely going to draw that one in because I don't really need it for the picture. But I do need it to find these high and low, upper and lower max and min lines. So if your vertical shift is 2 and your amplitude number is 2, that means your upper line is going to be at 4. And I definitely want to make sure that line is visible. If I do vertical shift of 2 minus the amplitude number, I get 0, and I definitely want to make sure that's visible because these are the boundaries for those branches of the secant function that we're going to draw. Okay, now what about the phase shift? Well, the phase shift is pi over 3 divided by 1/3. That's going to be pi over 3 times 3. So our phase shift is negative pi. It's negative because this guy's positive here. So it's the opposite of c divided by k. So negative pi means after everything's said and done, we're going to move this way just a little bit from the regular graph. Now, for secant, we want to talk about these asymptotes, because if we can get the asymptotes in place, then we can draw the picture. So since my first asymptote normally is at negative pi over 2, but that's not even on my graph, I'm going to slide over and I'm going to work on this asymptote that used to be at pi over 2. And I'm going to run through our process here. So I take the old asymptote, pi over 2, I divide it by k, which is 1/3, and then I'm going to add in the phase shift, which is minus pi. Well, pi over 2 divided by 1/3, that's 3 pi over 2, minus pi, and remember pi is the same as 2 pi over 2, so 3 pi over 2 minus 2 pi over 2, that's going to be pi over 2. My new asymptote is in the same place as my old one, which is pi over 2. Now pi over 2 is actually in between 0 and pi, so it's in a kind of a weird position there. Don't panic. Now, once I locate that asymptote, to get the next one, I'm going to go out to 6 pi. Actually, it's not the next one. It's the end of the cycle. I have to go 6 pi and figure out what that one is. So if I'm at pi over 2 and I go out 6 pi, I end up halfway between 6 pi and 7 pi. Now that's the entire cycle, but don't forget, smack dab in between there, we also have an asymptote where the branches switch. And that's going to happen straight in between. It's at 7 pi over 2, which is between 3 pi and 4 pi. Okay, so now I've got these regions, right? I have the regions that are above the red line and between the green lines, and the region that's below the lower red line and between the green lines. The only thing I have left to do is figure out where in the world this function is going to start. So keep in mind that each square is pi and that the entire period is 6 pi. So because we are doing a phase shift of negative pi, my vertex point for that first branch that's on top is going to be shifted over. Normally, because cosine starts high on the x-axis, that vertex would be here at 4. But we are shifting over a pi, so it's over a square. So that thing's actually going to be here, and this curve was going to go like that. So I don't see much of that top branch at all. And then remember, once we hit the asymptote, we shift down to the other branch. So now we're way down here, and this thing comes up, and it's going to hit at 2 pi, halfway between the two asymptotes. I didn't draw that very well, but that's where that one's located, and that's a bottom branch. And then up here we'll have another one, which is our top branch. And then over here we'll have another one, which is our bottom branch. And that's basically the curve. We don't quite get to the next asymptote because it's off the grid, but these blue sections of graph, these blue branches, are what the secant function looks like. This stuff is not easy to execute. It takes practice, especially if the fractions get crazy, which for a couple of your assignment problems they do. So don't panic, give it a shot. Make sure you fill in the values on the side first, and if you can't quite get the graph, I can help you when I see you again, but please give it a shot. Okay, I hope this helped. It was a long video, but this is what we talked about in class today, and so you needed to see this if you were gone or working online. Hang in there, and if you need something, just let me know. Take care.